last but certainly not least, we have Elena Timofeeva, who is founder, chief operating officer, and director of R&D at Influent Energy, and she'll be telling us about nano-enabled new energy storage paradigms, high energy density pumpable liquid batteries.
All right, thank you, Matt. Thank you, everybody. My pleasure to be here and present on results and vision that our company, Influent Energy, had been working for a while. So I feel very lucky to be preceded by the speakers today. I was like, oh my gosh, bingo, bingo, bingo. So I don't have to tell you a lot of things that I was going to tell. So the energy demand is growing. Luigi just showed us that it's not going to go down, and we absolutely need to transition to some sort of mix with renewable energy. So we've been, I want to get a little bit of the history where this is coming from. I worked at Argonne National Lab for 8 years, and in 2009 I started this research on the nanoelectric fuels. And in 2014 we formed a company, and since then we've been supported by different funding agencies, by government, through grants and all. And we, in a sense, we've been lucky not to having tell anybody what we're doing. But so by doing that, so we found our mechanism of funding, and we didn't have to spend time going around and telling everybody what we're up to. But right now, our maturity and kind of where our technology is at make us accept the fact that, yes, we have to tell everybody what's possible. So before I dive into our technology, I just want to remind everybody that hydrocarbons have quite a bit different delivery scheme compared to electricity, right? Hydrocarbons are liquid, and the first two talk kind of implied some unique features of liquid that can be found in solids. And the fact that we can pump them, truck them, deliver through like distribution networks is quite unique. While if we are doing with electricity generated somewhere, we need to build a grid. And grid is sort of, doesn't store energy, it delivers energy. So the storage mechanisms are needed. And most of the mature and available solution right now is lithium-ion battery. So, and it's very exciting that we finally start seeing technology breakthroughs and the wind farm being supported by lithium-ion batteries, but to be honest, it doesn't look like it's going to work on a really large scale, because just for the month of February, this is the headlines, right? So what is being realized now is like lithium-ion batteries, while being so mature and ready for us to adopt them, they have pretty serious safety issues, right? So on one hand, we have a meltdown of the energy storage plants. On the other hand, we have a ship full of electric vehicles that caught some sort of condensation of the salt water and started on fire. So lithium-ion batteries, cars that are being charged in the houses starting to catch on fire. So, and the problem is the fire is so toxic, you can't just wash it off and continue going on. You have to essentially rebuild. And insurance companies start taking note of it. And some areas have seen increase in insurance for homeowners as much as twice for those who have electric vehicles, and they charge them at the houses. So essentially, the point I'm trying to make is lithium-ion is a great intermittent solution, but for large-scale storage and implementation of the renewable energy, it's not going to work on a large scale. So we have infrastructure issues. We have a supply chain issues because of the materials that are being used. We have big safety issue, and the energy density of lithium-ion, even though it's the best out of all the batteries out there right now, it's nowhere near, it's orders of magnitude less than oil. So the question is, like, while oil is bad, right? If oil is so great, and in reality, yes, oil compared to any batteries wins 100 times, 10 to 100 times. And some can say, okay, there are new battery technologies that are coming online, but even then, they're not going to be able to solve problem completely because we're still going to run into infrastructure issue. And even if safety is addressed, we still run into issue with the supply chains. So with all that said, I would like to present you the idea that instead of opposing fuels and batteries, we can try thinking about, let's make fuels out of batteries. And this is an approach that we've been developing for all these years. So many of you probably heard of flow batteries. It is a proven technology. Vanadium redox flow batteries are out there. And like you probably know that they're loose towards, compared to lithium-ion on energy density. And the reason for that is flow batteries, I'm briefly going to explain how they work. They have liquid electrolytes, cathode and anolyte, that are stored externally to the extraction device, the stack, and they can be pumped in through the stack to extract energy and put energy back into the liquid, right? But the traditional flow batteries are energy density is limited to solubility of salts, right? So we can go above the saturated concentration of salts, and the nature doesn't allow us to overcome it. The solution that we came with is using nanoparticles instead of ions, dissolved ions in a solution, and with nanoparticles we can load up to 88% of solids in a liquid and maintain it in a pumpable liquid form. So in fluid energy, taken essentially a solid battery cathode anode materials and a flow battery concept, and we merge them together. So now we have a liquid electrical fuels that can be recharged in the flow battery format. So I have to say that we tried different chemistries and narrowed down on the chemistry that uses water-based electrolytes. First of all, because it's cheap, but second of all, it is non-flammable, and flammability is a really big concern for a lot of large-scale industries. So we do use abundant, inexpensive materials, and because of that, we can be cost competitive with lithium-ion. We have a superior supply chain approaches. We don't need lithium, and we are safer for users. So you probably wonder where we stand, like how far can we get with the water electrolyte? So, but in reality is that if you scale everything down to system level, meaning the pack that you place in the car with all the infrastructure that goes with lithium ion, it is, and with the ability of load our liquids with a lot of nanoactive, electrochemically active nanoparticles, we can match our energy density to lithium ion, right? And because of the abundance of materials, we can, like the cost is not a problem at all. So we have two chemistries in works. We call it Gen 1 and Gen 2. Gen 1 is something that I will be focusing on right now, but there's a development that is starting towards Gen 2, and Gen 2 would be able to really bypass the solid state and produce a technology that would be able to power airplanes and such. So we call it nano electrofuel. I mentioned it, but I didn't call out the abbreviation. We call it NEF, nano electrofuel. So essentially, it is the nanoparticles, cathode anode nanoparticles, dispersed in electrolyte, right? So in our NEF technology offers a rechargeable, non-consumable, so we are non-combustible and non-flammable solution, energy storage solution. So, but I started with comparing our technology to the batteries. And quite often we fell into this trap when people know about lithium-ion batteries and there's like, well, how do you compare? And we say we're kind of the same, maybe better on volumetric, but the energy density price, we are there. But what I would like to deliver and kind of put your mind on is that our technology is more than just the better batteries. Because it is liquid, because it can be used outside of the grid, can be delivered, trucked, pumped to whatever destination, and it sort of inherits the delivery routes that oil has, we essentially, with this fluid battery, fluid electric fluid fuel, we can simulate the grid at scale. When we have this fluid everywhere, we can create an alternative to the grid, right? So we don't need to build a huge infrastructure that has to be matched up and all. So we can deliver this fluid to where it's needed, deliver it through trucking like we deliver oil, right? So it could be used locally. You can charge it in your location, use it for your own vehicle, or you can have more generalized locations for this. So introducing something like that is pretty challenging because we're not just making a material that is better, that can be put into the production of the existing batteries. Essentially, we have to deliver like the whole system so people believe us that's possible, right? So we need to have a mobile platform that would be using our fluid. We need a refueling apparatus that would be able to pump fluid in and out of the vehicle like we do with the gasoline. And then we also need a recharging platform that would allow us quickly charge fluids from the grid or a power plant or, wind farm. So with that, I just want to tell you that we've been at it for more than 10 years. It started in 2009. And this is a core founding team. As of now, that's what we do at our lab. So we are located here in Chicago, right? And we have to do everything as I mentioned. We start with the synthesis of our nanoparticles, with the manufacturing of our devices, with optimizing the fluid dynamics within the stacks, manufacturing those stacks, and having to build custom battery control systems that would optimize the performance of the fluid. So I have to say, a proud moment is that putting the 500-liter reactor online so we can produce sufficient amount of fluid for all the demonstrations that we're doing. This is a video that I'm going to run for you, and it's been taken a while back. So this is essentially, but it's very exciting. I hope there's a little bit sound left. I hope it's not going to be overwhelming. So essentially what you see here is our tensile stack and the fluids that are circulating through the device, right? And we have a tether going towards a vehicle. So we can we're very excited to power our first vehicle. So I will tell you where it's at right now. The other question that we often asked, and our sponsor insisted that we film this because it was obvious to me it's not going to burn or anything, but people want to see how it reacts with the water, with the fire. So this is our flammability test. So this is just a napkin burning, not a marshmallow. It just puts out a fire like water. So essentially, it is a little dispersion of metal oxide nanoparticles and puts out fire. This is anode fluid. This is cathode fluid. So that's our flammability test. So obviously, when the two fluids are leaked out, there's fire. You can essentially feel confident that it's not going to catch. So the other idea, like people's like, oh, well, this is just separate cathode, separate anode, but what happens when you put the two fluids together? They both carry charge, they can participate in a reaction. And this is essentially equivalent of the puncture test for lithium-ion batteries when we have a shortage between two. So on the, for you it will be left-hand side, you see, or right-hand side. We see a lithium-ion battery puncture test that we borrowed from the available public spaces, and this is our equivalent of puncture test with two liquids. I want you to pay attention to the temperature. The room temperature is 22 degrees. And when we mix the two fluids, so you see that the temperature went up by 4.5 degrees. While the lithium-ion battery smokes and all, we don't have smoke or vapor, nothing. It just reacts into something intermediate between cathode and anode charging. And if the anode is air sensitive, and if it sits in the air, it slowly starts oxidizing. So that's pretty much puncture test. So I want to also tell you, I mean, I hope I made you appreciate how difficult it is for bringing something like this online, right? Because nobody needs it. Well, we want everybody understands that it could be interesting, but immediately nobody needs it, right? So there's like, we have to build everything to make sure people appreciate the vision and where we're going with it. So we were able to leverage non-dilutive funding for commercialization so far. So like 6 years in the development. So currently we're funded by NASA, Air Force, and DARPA. And if you look at the big vision that I described before, is that the DARPA is helping us to build a mobile platform that would be use this type of battery that would be placed on a vehicle. Then Air Force is funding refueling aspect of it and kind of more global vision of recharging and refueling. And NASA is interested into the charging aspect of it. Can we rapidly charge and discharge fluid? And from fluid, we can go towards charging lithium-ion batteries. Actually, if we can rapidly charge the fluids, then we can dump the charge back to the lithium-ion batteries, but while transferring the fluid back and forth. So it wasn't obvious when we started, but now it makes more and more sense what we did. So this is our DARPA project. It will be completed by the end of this year. So what you see is here we'll be building a mule system that will be placed into this floor scrubber by Tenon. They are our commercialization partner. So we built this battery. It's a drop-in replacement that has 36 volts, 70 amps, 15 kilowatt hours, and demonstrated and tested with this utility vehicle. So why utility vehicle? It was the easiest thing we can get onto, right? So lead acid batteries out, our battery in, go. So, and they have a pretty broad power needs from just moving forward to scrubbing and all the other things that require higher power. So it would be perfect first testing on the vehicle, and it could be our first market if they're interested in moving forward with it. So the NASA Rapid Charger is a little bigger, so to say. It will be 120 volt, 250 amp, 30 kilowatt system. So it's also due by the end of the year. And you can see we are testing 10-cell stacks at this point that are matching the size. The pickup truck is presented for reference, how big it all gonna be. So the idea here is that the stack itself, the stack size is proportionate to the current that we can get in or out of the fluids, right? So if we have really big cells and flash small amount of fluid by them, we can charge fluids a lot faster. While in actual vehicle, you would want to optimize your cell size to the power requirements so you can have a higher energy density. So there's optimization in the vehicle for vehicle needs, but if we have a big charger, we can just kind of like flush fluids by the stack and it's charged in a single pass. So, and this is another demonstration that is going to be coming online. And for Air Force, we are kind of combining recharging and refueling concept, right? So here, how the system would look like for a so-called refueling pod. Since it was designed for Air Force, it is fit onto their standard airplane pallets, right? So it can be carried in. It's less than 10,000 pounds, 450 kilowatt hours. And what I would like to bring, again, to your attention, that the voltage we can build through adding more cells to the stack, while the energy storage itself is a function of how big are the tanks we're going to have. So we can optimize, again, for the range for the vehicles. Like Julie was saying, they just add another tank on the vehicle. If the energy density is not as high, we can charge faster if we have a bigger charger, bigger charger cell. And then a speed of refueling, how fast your vehicle can dump the discharge fluid and put the charge fluid in, is going to depend on the function of the pump size. So this is our vision. This is a conceptual design right now. So we've been selected for phase 2, where we're going to build not 450 kilowatt hours, but a little smaller version of this, to be able to demonstrate that we can have a vehicle, we can have a recharger, and we can have a refueling all put together and operating as a system. So this slide again summarizes the efforts that we have going on. And the next slide is more towards where we're going. What do we want to see in the future? So what we're going after is a closed energy cycle ecosystem. So when we would have vehicles that would be running on the NEF flow battery, so we can have a charging pods connected to any source of energy. It could be renewable, it could be traditional energy, that would be delivered to the charging pod, and then vehicles would come to the charging pod and refuel in 3 minutes, just like with gasoline. So in this convenient format, no plug-in, no nothing, just a fluid swap, essentially. And then there is a cycle life to the fluid, which is about, we anticipate 5,000 cycles. But when it comes to the end, because it's liquid, it can be easily extracted. We can send it through local recycling, refurbishing, and reusing at local manufacturing. So once fluid is delivered to your fleet or ecosystem, it's going to circulate within there, right? So you don't need to deliver new. You can build a similar ecosystem in the next location. So this comes to idea about the manufacturing that can be also done locally, and fabrication that can be done locally. You don't have to transport it. It uses abundant materials, so we can use it forward. So our next steps are, besides the completion of this demo project that we're working on, is to really pick a commercial platform. We haven't decided on it yet, and demonstrate this completion of the vision. So, and from there on, with all the other efforts in introducing renewable energy sources, we can secure our energy future. So thank you. I want to point you to our webpage. We recently updated it. There's a lot of information there, and I'll be happy to answer questions.
Thanks so much. We do have one from online, which I'll ask first. What are the perspectives on the relative costs compared with other batteries?
Well, as I mentioned, we are targeting like $100, $120 per kilowatt hour, and that's at the lowest projection for lithium-ion batteries. So we like cost competitive with lithium-ion batteries, with lead-acid batteries and such. Gen 2, can be half that price. So.
Okay. Back of the room.
Hi.
Hi.
So for the widespread implementation of this technology, it sounds like you need to manufacture or produce a lot of nanoparticles.
Right.
So how scalable is your process of making nanoparticles? And are there any other bottlenecks for the scalability of this project?
Yeah, that's a good question. We do work on scalability from the very beginning. Right now, what we're using, I'm going to just bring up this slide with the picture. It's a single pot synthesis. We do batch production. We haven't necessarily looked into the continuous production. This is our apparatus for nanoparticle production. So I think it's scalable. You know, I will be able to tell you more later. So right now we're looking with the subcontractors who are experts in scaling up, and they are giving us advice on how to improve the reaction and all. So at this point, that's where we're at. We have pretty high confidence it's scalable, but
For the next in-person question, there's an online question that kind of is on the same trajectory here. And they ask, what are the environmental impacts if there was a major spill of this material, uncontrolled out in the street or something?
right. So as I said, it's earth-abundant materials. So like iron oxide, magnesium oxide. There's an alkaline electrolyte in there that involves certain caution, right? But because it's high solid loading, they evaporate pretty quickly, and you can collect the spill easily. So I don't think, like from the big picture, like we're not going to anticipate fire. We're going to anticipate some heat up when two fluid mixed up together, charged fluid mixed up together, but then they dry, and we have a powder left. So we collect the powder.
Thanks. Next question in the back.
Really exciting technology. I was curious, the energetic cost of producing the battery and how many cycles or the fuel and how many cycles it lasts. I'm wondering if that's something that's improving or getting worse with the iterations, and if you've thought about that.
Right. So as I mentioned, we anticipate the fluid lasting like 5,000 cycles, right? And it can be refurbished from there on because it's elements dispersed in liquid. We can reprocess them and make another fluid. As far as the processing cost, are you interested in like a carbon impact or something like that?
Well, I guess carbon and also energetic to produce it.
I see. To be honest, I'm not ready to answer these questions. Our goal is to get it out there, validated, and then see how we can optimize it. Thank you.
Thank you.
Go ahead.
Okay. Hello, nice talk. Thank you.
Thank you.
Is my understanding of flow batteries that you need pumps to circulate the anode and cathode liquid?
Right.
What is like the energy requirement of those pumps, and can the battery like pump itself, I guess is my question.
Right. So our power requirements for the pump, they use like 1 to 2% parasitic losses, depending which mode you're going to use, right? So we have a continuous mode where we can constantly pump in fluid in, but there's also intermittent mode when we just refill the stack, discharge it, move on, discharge, move on. So this is more energy economic method, but even with a continuous mode, there's a, just 2% losses on pumps. So we can live with that.
Hi. So I understand that you addressed the impact of large-scale spills and how you can quickly address those. I'm wondering, have there been any studies on toxicity to the human body of the nanoparticles that make up NEFs?
Right. So I worked with nanoparticles for all my career. The toxicity of nanoparticles have to be considered how they got into our body, right? So if they are airborne, they're more toxic, right? They can be inhaled, settled in our lungs, and then cause all sorts of concerns and issues. But when the particles are contained within some sort of media, like electrolyte, or then when it cakes up, it will be composite with alkaline and KOH all together, so it never really gets airborne unless you start spraying it out, like, and dry it out. So as far as the digestion goes, I mean, the cathode is, right now for Gen 1, cathode is a little more of the concern, but just don't drink it. As far as the toxicity goes, anode is like iron-based, so a little iron. They recommend using cast iron as a source. So, but generally, we are targeting pretty non-toxic and earth-abundant elements. So we have several versions of cathode. One is manganese-based. The other, like the green one that you see here is nickel, but it's just because it's easier to get working. So that's a plan. But Gen 2 would not have anything toxic at all.
Thank you.
Sure.
And maybe time for one more, possibly two.
Sorry if I missed it, but what is your current round-trip efficiency?
So we are at 90% efficiency right now, so, and we can probably do it better. So it is pretty good.
Gentleman down front, yeah, we have time.
Thanks for the talk. Since you mentioned a potential application in aviation, I'm wondering how's your electrolyte performance against low batteries, such as minus 50 degrees Celsius?
Okay, so we have, our battery is stable, negative 40 to plus 80 comfortably if it's well sealed and all. So minus 50, probably not, but minus 40 is okay. If we maybe use some sort of additional heating.
I see.
Right, so, but there's other, I didn't cover this all, but there's a lot of issues, issues that our battery solves for aviation. So there's an article that we've published with NASA. If you're specifically interested for aviation application, you can search it. I have reference on the web page too. So there's a EMI elimination because we can co-locate the stack with where application is needed, so we don't have to drag wires throughout the plane. There's a lot of benefits.
I see, thank you. But will the electrolyte froze under minus 40 degrees?
Minus 40 is still operational. Minus 50, it will freeze, so you would have to have some sort of a protection, so electrolyte wouldn't get to that temperature.
Makes sense, thank you.
All right, well, thank you very much. Elena Timofeeva, founder, chief operating officer, and director of R&D at Influent Energy. Now I know we're out of practice, but we do have 4 out of the 5 speakers in person, and you can come down and talk to them if you would like. Otherwise, I'm Matt Thompson, current chair of the Forum on Industrial Applied Physics, and this concludes session A15, Future of Energy. Thank you very much for coming.